Hey everyone. So today we're going to be talking about nuclear chemistry. So it would be probably a good idea for you to have the graphic organizer out and following along. You're probably also going to need a calculator today. So let's go ahead and get started. One of the things that I think is kind of funny about nuclear chemistry is that whenever I heard it in the past, I was like, nuclear explosion, like big, right? And I never really made the connection between nuclear chemistry and the fact that this is actually the chemistry of the nucleus, the center of the atom. So when you hear the word nuclear, it means that we're studying the chemistry of the nucleus. Now, one of the big words that kind of comes up in nuclear chemistry is radioactivity. When you see this, it's referring to the spontaneous disintegration of the nucleus of the atom. Spontaneous means it just happens on its own without any outside intervention. When a nucleus decays, high energy particles tend to be released or emitted from the nucleus, and they're just ejected out into the atmosphere to react or do other things. So that's why, generally speaking, when we hear of radioactivity and decaying, those particles can interact with us in a bad way. An atom that does not undergo nuclear decay is said to be stable. Remember when we were talking the other day about stable versus neutral? Neutral means the atom has the same number of protons as electrons. Stable means the ratio of protons and neutrons within the nucleus will not allow for the atom to undergo nuclear decay. So stable is radioactive or not radioactive. Nucleons is really just a fancy word for any particle that's in the nucleus. Remember, these are going to be the protons and the neutrons. So a proton is a nucleon, a neutron is a nucleon. They're just an arbitrary term for something that is inside the nucleus. Remember, we still use the mass number when we are, the nuclide notation when we're identifying the isotope. And that's represented with the mass number above. So this is the mass number and the atomic number down below, atomic number down below. Don't forget that the atomic number is the same as the elements number on the periodic table. So this is uranium. Uranium is element number 92. And the mass number is the number of protons and neutrons. So for this specific element, if we're looking at the mass number, this is equal to the protons plus the neutrons, then 238, kind of an ugly 8 there, is equal to 92 plus what? All right, so we just have to do that subtraction there. That's going to be 146. So uranium-238 has 146 neutrons, 146 neutrons. What's that there? Neutrons. All right, so let's go ahead and move on. In this section, we have a few special nuclides and symbols that we just need to be very comfortable with. So I'm going to list those out here. You've seen this experiment over on the right-hand side before. It uses alpha particles. So we're going to define what an alpha particle is today. But first off, if we ever use an electron has the symbol 0/-1e. Neutrons are going to be a particle that we're going to be looking at, 1/0n. That alpha particle there is 4/2 alpha. That's the alpha symbol. Beta particle is 0/-1, and this is the beta letter. Now I want you guys to see here, 0/-1e, 0/-1 beta. What can we kind of think about? What do we notice when we are looking at those? Okay. And then the gamma ray, the gamma particle is 0/0, and then this Greek letter here is gamma. Now I want to point out that gamma conventionally is 0/0 because it's just high energy light, and light does not have any mass associated with it. It is not any matter, so 0/0 hopefully kind of makes sense. Now these conventions for us may seem like a little different, but I want to point out that the mass number on the top is the number of protons and neutrons. And down below, we normally have the atomic number. This can also be the charge. So for the electron, it's got a -1 charge. For the alpha particle, it's got a +2 charge. So that's essentially the notation there. So, in the world of chemistry, there's a really cool vocab word, and I know that you're probably hearing cool vocabulary. What? One of my favorite things about nuclear chemistry is mass defect. Mass defect. Mass defect is the difference between the mass of the nuclide, so the atom or isotope that we're looking at, and the sum of the masses of its nucleons. What's really fascinating about atoms is that when you take the individual proton and neutron and put them together, them individually actually is heavier than the isotope or nuclide that they make up. So essentially, there's some missing mass. There's mass that is unaccounted for when we're considering the mass of an isotope compared to the individual parts. For this, you have to know the mass of a proton and a neutron. I've listed them down below. The mass of a proton is 1.007276 AMU. The neutron is 1.008665 AMU. So for this, we need to consider the mass of each one of these particles. So let's go ahead and look at this here. Calculate the mass defect for the helium-4 isotope. So whenever we start one of these problems, the first thing that we need to consider is the number of protons and neutrons within the nucleus. So for helium-4, helium has an atomic number of 2. I found that number from the periodic table. The number of neutrons can be found by taking the nucleus, which is 4, and subtracting the number of protons, which is 2. So 4 minus 2 is 2. So this thing has 2 protons and 2 neutrons. So what I want to do is find the mass of the nucleons. I want to find the mass of the nucleons. The mass of the nucleons is going to be 2 protons times the mass of the protons, which is 1.007276. And I'm going to add the mass of the neutrons, which is 1.008665, and get that sum there. So 2 times 1.007276 plus 2 times 1.008665 to get the mass of the nucleons. Which is 4.031882 AMU. Notice that 2 protons and neutrons by themselves has a mass that is heavier than a helium-4 nucleus. That's weird, right? That almost doesn't make sense. So the mass defect is the difference of those two numbers. So it's going to be the mass of the nucleons minus the mass of the nuclide, which would be 4.031882 minus 4.002602. And this will be our mass defect here. So minus 4.002602. So the mass defect is the difference there. It's that missing mass. It's a very small number almost always. 0.2928. All right, excellent. So I'll go ahead and move on here. I want to point out that I do want you to try to determine the mass defect for carbon-13 on your own. There's a space on your graphic organizer for this. I will say that for this, you need to know the number of protons and neutrons. So for carbon, there are 6 protons always, that's the atomic number, and 13 is the mass number, so 13 minus 6 is 7. So with 6, you need to find the mass of 6 protons and 7 neutrons, and then take that and subtract the difference from the mass of the nuclide, But I'll let you go ahead and try that one out yourself. All right, so moving on. Nuclear binding energy. So what the heck is this missing mass? Like, where does this go? Why do we need to know this? And generally speaking, this comes from the nuclear binding energy. So follow along with me here. First off, the nuclear binding energy is the energy released when the nucleus is formed from the nucleons. So we have the nucleons by themselves, and then they come together to form the nucleus. Generally speaking, it's possible to calculate the nuclear binding energy using probably one of the most famous equations in the world. And the second I say famous equation, you're probably thinking about, okay, what famous equations do I know? That's right, E equals mc squared. What this is the energy required to hold together the nucleus. The E here is the energy required to hold together the nucleus, the nuclear binding energy, is equal to the mass defect. So that missing mass is converted into energy to hold together the nucleus times c, which is the speed of light. We use this value to compare the stability of different nuclides. So basically, the more stable an element is, an isotope is, a nuclide is, the higher its nuclear binding energy is. The slower the nuclear binding energy, the less stable it is. So as far as the nucleus goes, let's all consider what's inside the nucleus. We have protons and neutrons. Protons are positively charged. Now, generally speaking, when I have a positively charged particle coming near another positively charged particle, positive charges repel. They'll want to break apart and be free from each other. But that's not the case for the nucleus. We have positively charged particles very, very, very close. Why is this? Well, we have an incredibly strong force of attraction between nucleons that are very close, and we call this the strong force. This strong force, the strong nuclear force, is strong enough to overcome the repulsive forces felt between positive protons. I'll go ahead and change that really quick. I don't know why it says electrons, positive protons. So as we are looking at this, right, we have this positively charged particle, and it's really close to another positively charged particle. And when they're right next to each other, they feel once again the nuclear force, the strong nuclear force, which is strong enough to overcome that repulsive force between the positive charges of the protons. It's one of the strongest forces in the universe. So moving on, the last thing that I want us to consider is there is a sum of forces, right? While we do have positively charged particles, sorry, I keep switching in here, positively charged particles called the protons, we have a much larger sum between all of the particles because every single one of the particles feels the strong force. But the electromagnetic or electrostatic forces are only felt between those positively charged protons. So this is definitely able to overcome the repulsive forces felt between positive charges. So what essentially makes an atom stable, and really at the end of the day for you, my general chemistry students, is that I need you to know that there is a ratio between the protons and neutrons, some sort of magic ratio which allows for the atom to be stable. Generally small isotopes, we want a 1 proton to 1 neutron ratio. And as the isotopes get larger, we generally need more neutrons. The ratio needs to become closer to 1 to 1.5. Anything that has an atomic number that is bigger than 83 or a mass number bigger than 208 is radioactive. There's no getting around this. The nucleus is just too large. And one of my favorite vocab words, again, there's a lot of cool vocabulary in this section, is that there's actually a list of magic numbers of nucleons that makes the element more stable. For some elements, having two nucleons, whether that's 2 protons, 2 neutrons, or 1 of each, is more stable than 3 or 4. 2 is one of those magic numbers. There's actually a list of these magic numbers that you can find in your textbook or online. Really, at the end of the day, you don't need to know those, though. This is what we call the band of stability. Now, as far as the band of stability goes, you can see all of the black dots within there. These are a list essentially of every single isotope we've ever created. And the black dots are the only stable isotopes. So you can actually see here that most of the isotopes that we have created are unstable. The ratio of protons to neutrons just isn't great. We actually have two lines here. A 1-to-1 ratio where Z is equal to N. Z is the atomic number, N is the mass number. And or excuse me, N is the number of neutrons, not the mass number, is 1-to-1. And there's a higher band up here that kind of goes here where it's 1-to-1.5. Remember that for lighter nuclei like oxygen-16, the number of protons and neutrons are equal. The ratio of protons to neutrons is 1-to-1. For a little bit heavier elements like mercury-200, you have 80 protons and 120 neutrons. The ratio is 1-to-1.5. As the elements get heavier, you need more neutrons in the nucleus in order to help overcome the electromagnetic forces, the repulsive forces between the protons. So what does this mean? Well, if you don't have that right number of protons and neutrons, if you don't have that right ratio, then the atoms do undergo nuclear decay. They go ahead and decay and break off parts of themselves until they are stable, until they are happy, if you will. The first type of radioactive or nuclear decay that we're going to look at is alpha decay, where a radioactive element will essentially lose 2 protons and 2 neutrons. An alpha particle is another word for a helium nucleus, which once again is just 2 protons and 2 neutrons. And the radioactive element can quite literally eject this from an unstable nucleus. One great example is the radioactive decay of uranium-238. It will eject 2 protons and 2 neutrons from the nucleus to make thorium-234, which itself is also radioactive. So it could actually go through this process again, where let's say we have uranium-234, which has an atomic number of 90, undergoes alpha decay. So that alpha particle is 4/2 alpha. And then you can actually continue this until you get a stable nucleus. So 234/90 yields 4/2 alpha. So this kind of acts like a equal sign. It's algebraically equal. So 234 equals 4 plus what? 230. 90 equals 2 plus what? This is going to be 88. An element 88, I believe, is radon, but this is why you have your periodic table. It's actually radium, so this would be Ra. There you go. So that's how you would approach these nuclear reactions, if you will. Here's a good example. Basically, here's our radioactive nucleus. It quite literally chucks out an alpha particle, which is 2 protons and 2 neutrons. The next type of radioactive decay that exists is the beta decay, where a beta particle is ejected from the nucleus. A beta particle is essentially a high energy electron. It is just an electron. When doing this, essentially a neutron is turning into a proton. So we have, once again here, I'll show you guys, a neutron, which is 1/0n. Remember, that's the symbol for neutron, turning into a proton, which is 1/1p. And essentially the only way that we could do this is by ejecting this electron. So we're changing that ratio of protons and neutrons within the nucleus. One of the most common examples of beta decay is carbon-14 decaying into nitrogen-14. Carbon-14 is one of the most famous radioactive isotopes. We use this to date living or unliving things. If we find bones, or pots or clothing, we can actually determine fairly accurately how old those bones, clothing, pottery is or are. Once again, the beta decay quite literally is the ejection of a nucleus. On the inside of the atom, what's happening is the neutron is turning into a proton and ejecting the electron with a high amount of energy. That little v here is velocity, so there's a lot of electron velocity. Another way that an atom can decay or change is electron capture. What essentially is happening with electron capture is an atom will take one of its core electrons and combine it with a proton to turn it back into a neutron. So essentially, this example here is we have potassium 40, K40, takes one of the electrons that are just kind of floating around outside the nucleus here, and combines it with this proton here and turns it into a neutron. Every electron capture produces gamma radiation. I'll go ahead and say that, all electron capture produces gamma radiation. Gamma radiation, remember, is high energy light, and it's kind of dorky, but hey man, this is what turns the Hulk into the Hulk, right? Bruce Banner into the Hulk. So every time this process occurs, gamma radiation is produced. Half-life is referring to the amount of time it takes for half of a radioactive substance to decay. This is a very specific and constant value. For example, carbon-14 has a half-life, carbon-14 has a half-life T1/2. This is the symbol for it, of 5,730-ish years. Sometimes you see 5,715, depending on the textbook, right around here, years. So essentially, if I had a 100-gram sample after 5,730 years, I would have 50 grams. After another 5,730 years, I'd have 25 grams. And basically, after every amount of 5,730 years, you would have half that sample remaining. So how could I approach and look at a problem type that looks at half-life? Carbon has this much half-life. How long does it take for a 322-gram sample to decay to 40.25 grams? Well, all you really need to do is take your initial mass, your initial sample, which is 322 grams, and cut it in half. We know that each time we cut it in half, 5,730 years has gone by. So 322 divided by 2 is going to be 161, I believe, but I'll double check. 322 divided by 2, yeah. So 161. So we know that this took 5,730 years. Cut this in half again, and we get 80.5. This process took 5,730 years. And then one last time, and we'll see that there's 40.25. That's another 5,730 years. So basically, 5,730 times 3 gets us 17,190 years. Basically, this is how long it would take for my radioactive carbon to decay from a 322-gram sample to 40.25 grams. This process, once again, right here, is determined by just taking your initial mass and cutting in half over and over and over again until you get your desired mass. So that's essentially it for today. If you guys have any questions, feel free to shoot me an email, and I will provide a couple extra videos to help you understand nuclear chemistry. Thanks.